Newton's cognizance of gravity was adequate to empower us to travel from the Earth to the Moon. Have you at any point wound up muddled in the determined march of time, contemplating whether our grip of it is just the outer layer of a huge, worldly chunk of ice? At its core, his knowledge isn't simply a speculation. A key could open the riddles of the universe, divulging a cosmos more perplexing and dazzling than we ever dared to consider. How does Brian Cox's new speculation challenge our customary impression of time? And what might the possible implications be for our understanding of reality? Join us on an intriguing journey through the passageways of time itself as we explore Brian Cox's recently unveiled, momentous hypothesis regarding the essence of time in the colossal universe surrounding us. Secrets await discovery, and some of these riddles relate to fascinating aspects of time and gravity, both imperative parts of our reality. Imagine a world where time behaves strangely, where it can either decelerate or accelerate. Moreover, the force that keeps us anchored to the ground might not be as it seems. This is the realm of Albert Einstein's theories of relativity, where our understanding of time and gravity takes an extraordinary twist. Albert Einstein, a renowned figure, provided us with a novel perspective on the universe through his theories of relativity. His work laid the foundation for understanding how time functions in different conditions, particularly when moving at remarkably high speeds. Everything began in the early 20th century when Einstein proposed two groundbreaking theories: the special theory of relativity and the general theory of relativity. The special theory of relativity, introduced in 1905, transformed our understanding of space and time. Simply put, it states that the principles of physics remain consistent for all observers who are not accelerating, regardless of their motion. This theory introduces the concept of relativistic effects, including the well-known idea that time can dilate or slow down under specific conditions. One fascinating thought experiment used to illustrate time dilation is the light clock scenario. Imagine being inside a rocket moving incredibly fast, almost at the speed of light. Inside the spacecraft, a beam of light bounces between two mirrors perpendicular to the direction of travel. According to the laws of physics, the speed of light is constant for all observers, meaning the light beam should appear to travel a longer diagonal path. The time it takes for the light beam to complete its journey should be identical for both the observer inside the spacecraft and the one outside. However, since the path appears longer to the external observer, it seems to take more time for the light to travel. This perceived time difference between the two observers is what Einstein termed time dilation. Time slows down for the moving observer relative to the stationary one. Understanding how phenomena behave when moving at high speeds, known as relativistic effects, is not just a theoretical concept. Scientists use enormous machines such as particle accelerators like the Large Hadron Collider to push particles to incredibly high speeds, nearly as fast as light. When objects move at such speeds, we must account for how time behaves uniquely to make precise predictions and measurements. Albert Einstein formulated the special theory of relativity in 1905, revolutionizing our perspective on the universe, particularly concerning time and motion. This theory challenges our intuitive understanding. It asserts that the laws of physics remain consistent for everyone, even if they are in motion. This contradicts our everyday experiences, where we assume that if something is already moving and we add more speed, it simply accelerates further. However, Einstein's theory states that there is a maximum speed that nothing can exceed: the speed of light. In this framework, events that appear simultaneous to us might not appear that way to those moving close to the speed of light. Another concept emerging from this perspective is length contraction, which suggests that if an object is moving, it appears shorter in the direction of its motion when viewed from a stationary position. Then, there's the famous equation E equals mc squared, which illustrates that energy and mass are interchangeable. This is crucial for understanding how subatomic particles behave when moving at high speeds, as well as for phenomena like nuclear reactions when atoms split. In reality, special relativity isn't just a complex theory. It plays a role in everyday applications like GPS. When GPS satellites transmit signals to your device, they are in motion, and because of this movement, time behaves slightly differently for them. If we failed to account for this time dilation effect in GPS calculations, your navigation could be significantly inaccurate. Thus, Special relativity informs us that time isn't uniform everywhere. It depends on how objects are moving. This idea challenges our conventional perception of space and time. It suggests that our traditional understanding of the universe might be slightly distorted. According to special relativity, time is not static. It is influenced by motion. Certain fundamental concepts, such as the constancy of the speed of light and the relationship between energy and mass, have been confirmed through countless experiments. But there's more. Enter Albert Einstein's general theory of relativity from 1915. This theory delves deeply into the connection between gravity and the structure of the universe. It disrupts the outdated notion that gravity is merely a force pulling objects from afar. Instead, it demonstrates that gravity arises because space-time itself is curved or warped. It's like saying, hey, gravity isn't some mysterious force. It's simply the natural way things behave in the universe. According to Brian Cox's interpretation, general relativity requires us to view the universe as a four-dimensional entity, merging three spatial dimensions with one dimension of time. Within this framework, massive objects such as stars, planets, and even ourselves affect the very fabric of space-time. Reality is shaped around objects, and this molding is what we see as gravity. Imagine space-time as a tremendous, adaptable cover. When a weighty object like Earth is placed on it, it creates a space. If you position something smaller like a ball near Earth, it will move toward this downturn. This mirrors how objects respond to gravity, not as a mysterious force, but rather as a reaction to the curvature of space-time. General relativity offers a robust explanation for how celestial bodies navigate our solar system. For example, planets orbit the Sun in predictable paths, including Earth's elliptical orbit. According to Brian, this contrasts with the outdated idea of gravity simply attracting objects, which struggles to explain planetary motion. The groundbreaking idea is that space-time is curved like a flexible fabric, aligning more precisely with our observations. A pivotal event that validated the accuracy of general relativity occurred during a solar eclipse in 1919. Sir Arthur Eddington led a team to observe how light from distant stars bent as it passed near the Sun. According to the theory, the Sun's mass would cause the starlight to curve slightly. During the eclipse, the observations matched Einstein's predictions, affirming the theory's credibility. Just as motion can alter our experience of time according to special relativity, gravity also influences time. In regions where gravity is exceptionally strong, time advances more slowly compared to areas with weaker gravity. So, if you were positioned near a massive object like a black hole, your clock would tick more slowly than one set far away from this immense mass. General relativity introduces black holes, regions where gravitational forces are so extraordinarily strong that nothing, not even light, can escape. The boundary around a black hole is known as the event horizon, serving as the point of no return. Once an object crosses this limit, it is pulled into the black hole with no chance of escape. Einstein's general theory of relativity has significant implications for the structure of the universe. Initially, he incorporated a concept called the cosmological constant into his equations, believing the universe was static. However, upon discovering its expansion, he regarded this as a major mistake. The idea of an expanding universe based on general relativity is a fundamental component of the Big Bang theory, which explains the origin of the universe. Another significant concept arising from general relativity is gravitational waves. These are disturbances in the fabric of spacetime caused by extremely massive objects moving rapidly, such as colliding black holes or neutron stars. In 2015, scientists at the Laser Interferometer Gravitational Wave Observatory, LIGO, directly detected gravitational waves, providing further evidence supporting Einstein's theory. Over time, researchers have conducted numerous experiments to verify the accuracy of general relativity, and consistently it has proven correct. Whether through observing planetary motion, the bending of light, or the detection of gravitational waves, general relativity has stood the test of time. While the idea that gravity is an illusion may seem surprising, especially since we experience it daily, it is common in physics to explore alternative theories. Scientists like Brian often challenge established concepts. Within the study of gravity, some question traditional views of this fundamental force. One idea that contradicts conventional gravity is modified Newtonian dynamics, MOND, which suggests that gravity behaves differently at lower accelerations, particularly in galaxies, without the need for dark matter. Instead of introducing unseen matter, MOND proposes that gravity strengthens at reduced speeds. Discussions about gravity also include the mysterious concepts of dark matter and dark energy, which were introduced to explain certain phenomena in the universe. Critics argue that these ideas are unnecessary and that alternative theories could adequately explain our observations. Some scientists who disagree with Einstein's theory of gravity pursue new directions, such as hypotheses involving unknown particles or forces that could modify or enhance our understanding of gravity. It is essential to emphasize that in science, new ideas are not dismissed outright. They are rigorously tested for validity. For instance, Einstein's concept of time within four-dimensional space, where time travel might be limited by the speed of light, has been creatively explored alongside ideas like wormholes and shortcuts. Stephen Hawking's chronology protection conjecture suggests that traveling back in time is unlikely from a physical standpoint. Ongoing studies and observations aim to determine whether these new theories can explain phenomena such as the force of gravity in ways that align with existing data. While many theories have been proposed, none have convincingly replaced the well-established laws of gravity. Questioning and testing established ideas are fundamental aspects of scientific progress, leading to further inquiry and a deeper understanding of the universe. Among gravitational theories, general relativity remains the most significant and effective. Despite facing challenges and alternative hypotheses, it consistently performs well in experiments, accounting for various phenomena such as planetary motion and the bending of light around massive objects. General relativity endures because it is comprehensive and explains a wide range of phenomena. As mentioned earlier, Einstein's special theory of relativity shows that time behaves differently depending on one's movement. Now, let's explore how this idea applies to real-world scenarios, particularly in space exploration. Space exploration is exciting but challenging, as the universe is vast, and according to Einstein's theory, the speed of light is the highest rate at which anything can travel. This presents a significant challenge for interstellar travel, even with advanced technology, due to the long duration required to reach the nearest stars. To understand what happens to time during space travel, consider the famous twin paradox. Imagine one twin stays on Earth while the other takes a fast journey to a distant star. Upon the space-traveling twins' return, they find that less time has passed for them than for their sibling on Earth. This demonstrates that they have effectively traveled into the future. Time dilation is crucial for space explorers. The longer the journey, the more time slows down. If astronauts were to visit nearby stars where time significantly decelerates, they could age more slowly than people on Earth. While this may sound like science fiction, it is a real phenomenon arising from the theory of relativity. Imagine humanity dispatching a crew to a star system not far away. Due to the vast distance, the journey could take many years. Even if they travel at high speeds, time would feel shorter for the astronauts on board due to the time dilation effect, while on Earth, a much longer period would have passed. Time dilation affects not only living beings but also technology. Computers and communication systems aboard spacecraft must account for time dilation to ensure accuracy and efficiency. High-speed space travel presents physical challenges, such as prolonged isolation, exposure to cosmic radiation, and psychological effects from being away from Earth for extended periods. In our daily lives, we can observe the implications of time dilation in the Global Positioning System, GPS. GPS relies on the precise timing of signals from moving satellites. Since these satellites experience time dilation, it is crucial to account for these effects to maintain accurate GPS calculations. Ignoring this would significantly undermine the precision of navigation systems. Now let's explore why time moves in a single direction. Time governs our lives in the universe, moving from the past to the present and into the future. This one-way movement of time is fundamental to our reality. But why does time exhibit this unidirectional nature? To understand this, we examine entropy, an idea that measures disorder or randomness within a system.